sufficiently smooth invertible, which is actually true for weak lensing. In fact, this mapping is very close to identical mapping, and so it's typically a well-behaved map from one plane to another plane. And this is how so this mapping is given by a 2 by 2 matrix, because we map a 2-dimensional plane onto a 2-dimensional plane. And this is how we wrote the 4 entries of the matrices. So it's a symmetric matrix. It has 3 degrees of freedom. It has 2 rotationally invariant quantities, kappa and the magnitude of gamma, which is given by the magnitude of this complex number. So this is something that we saw in the first day. Are you with me so far? Is it clear? Okay, so another way to write this commonly is to take out this 1 minus kappa out of this matrix and call gamma divided by 1 minus kappa as G. So gamma is what we call as shear, and G is what we call as the reduced shear. And this is done because what we observe in weak lensing is this G1 and G2 and not quite gamma 1 and gamma 2. But again, in the weak lensing case, kappa is very, very close to 0. It's not exactly 0, but it's very small. So G is approximately gamma, but let's keep the distinction clear. So shear is different from reduced shear, and it is given by this transformation. And this is just a way of defining another quantity. Now you can work out the determinant of this matrix, or more importantly, what is the eigenvalue of this matrix A in terms of kappa, G1, G2. Can you quickly work that out? So the easiest way to see is that this matrix can change with rotation, but the eigenvalues will not. So let me rotate this matrix so that G2 is 0. So you can assume G2 is 0, and then you can just read off the eigenvalues, which would be the diagonal ones, 1 minus G1 and 1 plus G1. But now I have also rotated it so that G1 is also the magnitude, and the eigenvalue should not depend on the component. So it should be 1 minus kappa 1 plus or minus modulus of G. So if you don't understand the argument, then you can work this out and you will get this for any G1, G2. But there is also another way of arriving at this very quickly, which is to take G2 to be 0 and G1 as the magnitude of G. Again, these are complex numbers, so we talk about magnitudes of numbers here. And once you get these eigenvalues, it's easy to get the determinant because that's just product of the eigenvalues. And again, in weak lensing, both gamma and kappa are small, so they are pretty close to 0. So we've talked for the past 2 days about what kappa means, its physical interpretation. So it has to do with the surface mass density, which is the actual 3-dimensional mass density but projected or integrated along the line of sight. So by now you should have you should know what this kappa represents. It represents this 2-dimensional mass density. And you've all been asking, what is this? How do I interpret gamma 1 and gamma 2 in a similar way? So the physical interpretation of gamma can be a little tricky. So what we instead do is to take kappa and give it a geometrical meaning, and then we will see the geometrical meaning of gamma 1 and gamma 2, and that is how weak lensing is also done in practice. It's done as a geometry and more than a physics, more than a physical perspective. So to see the geometrical meaning, let's set the modulus of G, or let's set G1 and G2 to be 0. So this is never possible in a weak lensing case. If G is 0, then kappa is also 0. But let's consider a generic coordinate transformation that is not given by a lensing potential, but little more general than lensing, just to understand the feeling of what different quantities mean. So when I set G1 and G2 to 0, the matrix A becomes just 1 minus kappa times the identity matrix. So how do you visualize this? What is the geometrical meaning of this factor 1 minus kappa? So what if A is identity? What if kappa is also 0? What happens to the mapping? Or what happens when you look at the source? Sorry? Attraction? Or contraction? Yes. Yeah, so that is if 1 minus kappa is smaller than 1. So then there is a stretching. But if kappa is also 0, then you get the exact same plane. The source plane and the image plane are identical. You see the image of a source exactly where it is. Yes.
Sorry, Arun. I didn't quite get why, if 1 minus kappa is less than 1, then it's a contraction. I didn't see it.
Sure. But if kappa is 0, do you see that the two planes are identical? The image plane is same as source plane, which means you see the source where it actually is. Nothing changes at all. Now if kappa is not exactly 0, so let's call this, so this is beta 1, beta 2, and let's call the position of this as some A and B. What is the position of the corresponding point in the image plane? You can use this matrix then. So this suggests that if you take, or in other words, so A takes from theta to beta plane. So this is just writing beta vector as A times theta vector. And this would mean beta 1 is 1 minus kappa times theta 1, and beta 2 is 1 minus kappa theta 2. So the corresponding point here would be A divided by 1 minus kappa and B divided by 1 minus kappa. And if this quantity is greater than 1, then this is closer to the origin than this one is. Yes, so it contracts. Or if 1 minus, so kappa can be both positive or negative. It's probably not easy to see given this definition. But remember that we cannot determine kappa exactly because there is this concept of mass sheet degeneracy that I talked about. If you place in a uniform block of mass between the source and us, there is no way you can measure the mass of that block. So kappa can actually be negative even physically speaking, because there is something and you don't account for it. So this 1 minus kappa, depending on the sign, acts essentially like a stretching. It can be contraction or it can be elongation, but it happens the same way in both directions. So both both the directions 1 and 2 get stretched equally. So it's just a magnification. So that's the geometric meaning of kappa. It stretches the coordinate axis. Is the geometric meaning kappa clear? It's just stretching, which can be contraction or expansion. Now, to see how G1 or the gamma 1 comes in, let's have kappa, let's set G2 to 0, but just have G1. Now what happens to this quantity? So I will have I will have 1 minus G1 here and 1 plus G1, and this becomes 1 minus kappa minus G1, 1 minus kappa plus G1. So you still stretch the axis, but this time you stretch them differently. So in one of them you stretch it by a factor of 1 minus kappa minus G1, and along the other axis you stretch by a different factor. Sorry?
Yeah, a multiplication?
Yes, but multiplying different numbers along the different axes. Sorry, what do you mean by will it be a multiplication?
Like 1 minus kappa times 1 minus G1.
Oh yes,
and
sorry.
1 minus kappa times 1 plus G1.
Yes, that's correct. Yes, that's correct, thanks. So the 1 minus kappa first does an isotropic stretching. That is, it stretches, I will just call it stretching. It can be contraction or expansion. I will just call it stretching. It stretches first isotropically, and then the G1 term, or the 1 plus G1 term, stretches anisotropically. That is, it stretches the horizontal axis by one amount and the vertical axis by a different amount. So what happens is, then if you have a circular source here, it can become a smaller circular source here because it has been contracted or expanded. So the size changes, but a circle remains a circle. But when you stretch the different axes by different amounts, the circle here gets stretched differently and it can look like an ellipse. So the shape has changed, or we can say that the circle has been distorted because of this G1 term. So that's what the shear does. It takes an object, it distorts the object. The kappa term does a size magnification. It can make the size bigger or smaller, but it doesn't change the shape. The G1 term changes the shape, and the G2 term will also change the shape, and we'll see how exactly it looks like. So this is the same image that I drew. Sorry, yes.
Are you saying that the kappa affects isotropically and the G not?
Yes. So kappa affects isotropically because the same factor in both directions.
In both directions, okay.
But the G1 does not, because it's 1 minus G1 in one of the axis, it's 1 plus G1 in the other. So if G1 is something like 0.1, then you contract one direction and you expand in the other direction.
That changes the shape.
Yes, that changes the shape. So it's like taking a circle, pushing it in one direction and pulling it along the other.
Okay.
So that's what happens here. So this contraction and expansion is along the horizontal and vertical axis when G2 is 0. When G2 is not 0, the same thing happens, but it can be at an angle. So this circular source can be stretched in a different direction, not along x and y, but along some axis which is given by phi. And this phi is exactly what we have when we write G as a complex number. If I write G as G1 plus IG2, so this is in Cartesian or XY form. I can also write this as modulus of G e power some angle, which will be 2 phi. So if this angle phi is 0, then this is a real number. So G1 is the modulus of G, G2 is 0, and that is what happened here. So we stretched or contracted along the x and y directions. If phi is not 0, then there is an imaginary part given by G2, and all this means is that stretching happens along a different direction given by phi and not just along the x and y directions. So G2 is to be seen as something that changes the direction, and you can see that the magnitude of this complex number G tells how distorted or how elliptical this becomes. The individual components G1 and G2 will tell the orientation of the ellipse itself. Is this clear so far? Yeah.
So when we were doing the vector plot yesterday,
Yes.
what was that we were doing exactly to generate those vectors? Like,
So those vectors were given. So these numbers G1 and G2 were given to you, and all you were doing is to plot ellipses like this, but you did it in a slightly different format. The length of the arrows or the vectors represented the ellipticity, how much was it stretched by. So if the smaller the length, the more circular it was. The size did not matter. So the length corresponded to this ellipticity itself, and the direction corresponded exactly to this orientation of this ellipse, or the orientation of this major axis with respect to our coordinate frames. So that's the geometrical meaning that we have for kappa, gamma 1 and gamma 2. And the way weak lensing works is to estimate this geometry from kappa 1 for gamma 1 and gamma 2, or G1 and G2. Estimate kappa as a geometrical quantity itself, and then use the other way of defining kappa, which is the physical way, using mass density, and that's how we get mass. So the practical gravitational lensing is converting geometry into physical mass quantities, and unfortunately gamma and gamma 2 only have geometric meaning that is easy to understand. You can have physical meanings, but that's a little complicated. But for this course, I would say if you understand the geometrical meaning of gamma 1, understand geometrical and physical meaning of kappa, then that is enough, I would say. Yeah, you had a question.
Yesterday activity, you gave us the G values, but in order to know the G values, do we have to know the real shape of the source?
To some extent, yes. So all those was already done when I gave the data vector. So later in some time we will see how exactly to measure this G1, G2. How do we define ellipticity for these galaxies? But that was already done and given to you. I don't know if this answers your question.
No, I didn't understand.
Okay. So wait for a few more slides, and then if you have this question, ask again. So we'll see how to exactly get G1 and G2, or the complex number G itself. So here's another easy way of seeing this. This is exactly what I said. So with kappa, the shape remains the same. A circle remains a circle, but it can get stretched or contracted depending on the sign of kappa. And with gamma, or gamma 1, which is the real part, it can either get stretched along the vertical direction or along the horizontal direction. Again, it depends on the sign of G1 or gamma 1. And if G1 is 0 and G2 is non-zero, then the stretching happens along a 45-degree angle. So it can be along 45 degrees or 135 degrees, or pi by 4, 3 pi by 4. This is when G1 is 0 and G2 is not 0. And that would, so G1 0 and G2 not 0 would correspond to G1 0 and G2 not 0 will correspond to phi being pi by 4 or 3 pi by 4. So when you have phi being pi by 4, then you have e power I pi by 2 here. So that's exactly I, which means you only have the imaginary part and no real part. And that means the stretching happens along the diagonal directions.
I just want to be sure. So if phi is 0, we have 0 stretching. Or
No.
We have
Phi is
stretching
0,
along the
stretching
axis.
along 0 or 90 degrees.
Okay, and if phi is different than 0, happens what is in the third column.
So
Third line.
yes, so if phi is non-zero, then the stretching happens along
Okay.
the phi direction, the
Okay,
phi
thank
direction.
you. That's all.
So if all the galaxies were perfectly circular in nature, to find this, oh, did you have a question? Yes, sorry.
Yes. So when G2 is not 0 and G1 is 0, so the stretching occurs along a diagonal, some direction.
Some
diagonal
direction.
But does it get squeezed in the perpendicular direction, or?
Yes, it always gets squeezed in the other direction because it occurs with different signs.
But if G1 is 0?
Yes, so this was the case where, so if G1 is 0, or if there is G2, then there is also this, okay, so the correct way of doing this is saying it gets stretched by 1 plus modulus of gamma in one direction, and it gets contracted by 1 minus g in the other, in perpendicular direction. If in addition, if kappa is significant, then there would be an overall stretching or contraction. So it could get stretched in both directions, or it could get contracted in both directions. But ignoring this term, the shear itself will always stretch in one direction and contract in the other direction. So we have separated this distortion into an isotropic part and an anisotropic part. The anisotropic part is always extension and compression. It always occurs in pair. So if we had these kind of perfectly circular sources on the sky, if galaxies were perfectly circular, to find this G1 and G2, all you have to do is to look how the galaxies appear, whether if they are elliptical. From the ellipticity you should be able to get the shear, and from the orientation you should be able to get phi, and you can get G1 and G2. It would be very simple, but that's not the case because galaxies are already elliptical as a rough approximation, and you take an ellipse and you distort it further into another ellipse, so you still have an ellipse. But we don't know the unlensed or the original shape of the image, and we want to find the transformation. So we have two unknowns, and we can only see how the lensed image looks like. So in order to do this, we first need to define an ellipticity of the galaxy itself, the intrinsic ellipticity of the galaxy. And we do it just like how we have this for shear. Again, we like complex numbers in lensing, so again we define a complex ellipticity, epsilon 1 or epsilon 2, or I'll just call it E1 and E2 so that it's simpler. And what this would mean is the magnitude of this complex number will tell the ellipticity of the shape, the intrinsic shape itself, and phi again will tell how the ellipse is oriented. Now this is without lensing, this is just a way of describing ellipses. And to exactly quantify this, we can see this in terms of axis ratios. So if there is an ellipse, here, you can define a major axis, and you can define a perpendicular minor axis. The standard terminology is to call the length from the center to this point as A, and from the center to this point as B. And the axis ratio would be the length of the major axis, or the minor axis, which would be 2B, divided by the length of major axis, which is 2A. And this is denoted by a symbol Q. So for a circle A equals B, there is no specific major axis and minor axis. You can choose any perpendicular axis, and Q is 1. So the axis ratio Q is 1 for a circle, and you want this to be of zero ellipticity. So there are various definitions of ellipticity, but I've taken one, which is to say it's 1 minus Q divided by 1 plus Q. So if Q is 0, as it is for a circle, it has zero ellipticity. And the more elliptical it becomes, this axis ratio goes towards 0. It can never be perfectly 0, but the smaller the axis ratio is, the longer or the more elliptical it is, and it will have a higher E value or the epsilon value. Again, this quantity is still bounded between 0 and 1. So it is 0 for a circle. It can at most be 1 because Q is still a positive quantity, but it is never perfectly 1. But the higher the modulus of epsilon is, the more elliptical. And the phi again talks about the angle of orientation. So if we define this to be the x-axis, and if this is the y-axis, this angle would be phi. But then this term here is always twice the angle, because you want this to get the same ellipticity if you rotate it by 180 degrees. If this was phi instead of 2 pi, then you will have multiply defined values for ellipticity. You can rotate this 180 degrees, you get back the same ellipse, but then you would have changed the sign of the complex ellipticity. So you don't want that, which is why we put in a factor of 2, 2. account for that. Yes.
I'm a little confused. We were working with planes that have angles beta 1, beta 2, theta 1 and theta 2.
Yes.
But there you're saying that phi is the position angle and it refers to the orientation of the major axis
Yes.
with respect to the x-axis.
So
which will be
so
the
this is
x-axis.
so this is independent of lensing. So forget the beta plane and theta plane for now. I'm just defining
Okay.
ellipticity. So okay, so since I'm also talking about the intrinsic ellipticities, you can assume I'm talking about the beta coordinate system. So this is beta 1 and beta 2. So we can call this as beta 1. This is beta 2.
Thank you.
But you can define ellipticity for an ellipse even in a non-gravitational lensing concepts. So I'm just saying that if you have a generic x-axis, y-axis, and you have an ellipse, this is one way of defining the ellipticity of an ellipse.
Thanks.
Yeah. So this is to give you a picture of how different values of E1 and E2 correspond to different shapes. Again, if E1 and E2 is 0, this point, then it's a perfect circle. For if E2 remains 0 and E1 is positive, then you have an ellipse stretched along the horizontal direction. And if E2 remaining 0 and E1 is negative, then you have this stretched along the vertical direction. And if E1 is 0 and E2 is positive, you have this stretching along a positive 45 degrees or pi by 4. And if E1 is 0 and E2 is negative, then you have this along 3 pi by 4 or 135 degrees. And for different combinations of E1 and E2, you can visualize how the shape of this ellipse looks like. Yes.
Sure. You say that the kappa was the surface density, right?
Yes. So that's the physical meaning or interpretation.
One can say that so the contraction and the elongation depends on the distribution of mass of the lensing.
Of the lens, yes.
So these g values depends of the orientation of the lensing or what?
No, not upon the orientation of lensing, but also depends on the position of the source and the lens.
Position of the source and the lens.
Yes. So if you recall, so this A matrix was specific to a particular image at an image location theta naught. So this is a general mapping from theta to beta, and what we've said is we'll assume that the mapping is smooth and we will linearize, so we'll do a Taylor expansion of this function beta as a function of theta. So this function essentially says you can give me an image position theta and I can tell where the source is beta. That is not necessarily a linear function of theta, but in a small range of values around the image we can assume it's linear. So that's basic Taylor expansion and then stopping to the linear term. So this matrix A depends on the source position itself, which means if you change the source or the image position, you will have a different A matrix, which means it will have different G1 and G2.
Okay, thanks.
Yeah. Or another way of also saying this, a circular lens will also produce, okay, then we should also go to this, if you remember the expression for gamma 1, gamma 2, we had a lensing potential psi. and gamma 1 was given by half of this. So if you have a circular lens, it will also produce a psi which has circular symmetry, or more specifically, these two quantities will be the same and they will be 0. So the gamma 1 will be 0 for a perfectly circular lens, and similarly gamma 2 will also be 0 for a perfectly circular lens. But again, neither the sources are circular, neither the lenses are circular. So in general you will have this G1 and G2. And it also depends on the orientation of the source and the lens. Any other questions? Okay, so again, what I mean as ellipse is, you will have a galaxy. So you can have, so they're not going to be perfectly elliptical, but you should be able to define isopods. So galaxies are not objects with very hard boundaries like perfect circle or perfect ellipse. You will have so you will have an ellipse or an elliptical. So you will have a brightest spot in the center, and this will correspond to some other bright isopode. That is, along the brightness is the same along this ellipse, and then a lower brightness along a bigger ellipse, and an even lower brightness along the outermost ellipse. So this will have a light profile saying that it's an extended object, and then at different area you will have different brightness. But if you draw all the points where the brightness is the same, to a very, very crude approximation, we say these are ellipses. But then there can be very, very irregular galaxies where you will not be able to find such an ellipse. The galaxies can look something like this. Okay, that's probably not very realistic, but it's very hard to define an elliptical isopode for something that looks like this. So we need to move on from this very specific definition of ellipticity that assumes there is a true elliptical nature to something more general that you can use for any image, even though they are not elliptical. So now we treat this ellipticity as just a complex number. They can have this physical meaning when the source is actually elliptical, but if they are not, we need to come up with a way to find a number for this. So that is done using what we call as the moments of a distribution. So if you've taken any course on mechanics, so have you had any basic if you say moment of inertia tensor, have you had any such courses in mechanics? So this would essentially be the same thing, where this I of x could correspond to a mass distribution, and then you define the moments of the mass distribution. So this can be done for an image or for a mass distribution, so on, and here in lensing we do this for images. So even though I may not be able to define an elliptical iso for every galaxy, I know the pixel values. I know what the brightness is at every x and y on the image. And then we construct what we call as a moment matrix in this form, that is defined in this way. So Qij would mean raise x to the power I, raise y to the power j, and then integrate over all the image pixels that you have. So in the case of an image, this would be a sum, but for a continuous function, this is an integral. And I and j can take any values from 0, 1, 2 all the way till infinity, but we will mostly focus on the small values of I and j. So under this definition, what is Q00? What does Q00 physically represent? Yeah, but if you evaluate that expression. Sorry? What's I? It's some number or some constant, and you raise x to the power I. Oh, sorry, that's the image pixel value. So if you will have, so if this is the image, if this is the x axis and y axis, you take a pixel here, and the brightness that you observe in this pixel is the I of x and y. So it's the flux in that particular pixel, or it's the, sorry? Yeah, so like intensity, yes. Or we just call this as the pixel value. It's whatever number that you have in a given pixel, which will correspond to the brightness or the flux collected at that particular point. So what is Q00 then? Yeah. It's the total flux of the object. So this would just give you the flux of a small part, this guy. And if an image should typically occupy several pixels, not just one pixel, that means it's very poorly resolved. So an image can look something like this. So this, let's say this is a galaxy. And then you have several pixels covering this. And if you add the pixel values or the intensities at all of the locations, you get the total flux or total brightness of this galaxy. Or you get the flux from which you can also get the magnitude of the galaxies. So Q00 has this meaning of the total flux itself. What about Q01 and Q10? Somebody else, not you, Miguel. What would these physically represent? Q01? Why? No. No, you're still integrating over all x and all y. So it cannot be just flux of single pixel. So not quite, no. Okay, so if I have an image here, and so whether I have a galaxy here or whether I have the galaxy here, Q00 is going to be the same because it's just about the total flux, and let's just call this as the origin. So I call the center of this pixel or center of this image as the origin 00, and it does not matter where I place this galaxy because for the Q00 there is no reference to x and y, and you just get the total flux no matter where you place this. But Q01 and Q10 will depend on where I place this galaxy, because now the x values, the x and the y values are very different for this galaxy compared to the x and y values of this galaxy. So now can you say what this should suggest? No. I mean, it is like a weighted flux, but what does that refer to? Yes.
Quick question: I and J, are there superscripts or are
They're
there?
powers. They're actual.
They are
You're
powers.
raised to the powers. So
Okay.
it means it can mean x squared, x cubed, and so on. Yeah.